All right, this is the last section, modeling with exponential and logarithmic functions. This is how we usually use this mathematics in the real world. We're trying to model how something's going to grow. This could be anything from stocks to investments to a business. And we genuinely want to see things work out, so we try to model it. And the process is we're going to solve some literal equations for a specified variable. We're going to create models for exponential growth and decay, and we're going to apply logistic growth models. So let's get through these. These are the last 10 set of slides. So here we're just solving for D, just the basics at this point. If there's something I'm looking for, can I solve for it? And the answer is yes. So again, I need to isolate my log, so I have just the log by itself. And in this case, I'm going to move or subtract 23.5 to both sides. 23.5. So I have S minus 23.5. And I'm going to put that in parentheses just because that's going to become important. And it's equal to 2 log of D. Now, I could bump that 2 up, right? Like we know we can do that. I'm not going to. I'm actually going to work it the other way. I'm going to simplify from here by dividing that out and dividing this whole thing. So now I have S minus 23.5, and I'm going to keep that in parentheses, all divided by 2, is equal to the log. Remember that log is base 10 of D. And let me reorganize it up here. I'm going to write the log first because that's the way I've been doing the crossing. And D is equal to all of this, S minus 23.5 divided by 2. And this is 10, so 10. This comes down. This goes over here. And this crosses over here. So 10 to the power of S minus 23.5 divided by 2 is equal to D. And maybe I'll clean how I write that a little bit. So I have S minus 23.5 divided by, that's 0.5 divided by 2. And my 10 is here. So this is 10 raised to that is equal to D. And I have solved for D. Again, I have another variable in here, so there's really not an easy way to solve that, to find out what that is. So I'm just going to leave it like that. And this is the answer. Okay, not too bad, just a straight solve. It's not an evaluate where you expect to get a value. This is a solve, so we're not necessarily expecting a value. So we're going to create models for exponential growth and decay. We're going to let y be a variable changing exponentially with respect to t. Usually t is time. We're going to let y naught represent our initial value. Whenever we have the 0 under below in the subscript, it's called naught, N-A-U-G-H-T. So let y naught represent the initial value of y when t is equal to 0. So that's our beginning, our initial stage. And this can be used to model population growths, population decays, decays of matter, decay of a company, and a actual industry. So this works for many different things. For a positive constant k, we're dealing with a growth. For a negative constant k, the model is decay. It's a decay. So here we're just saying that k is greater than 0 in this one, and k is a negative number here. Okay? So that determines whether we're looking at decay or growth. So suppose that at 19 years old you win $100,000 playing the lottery. If you would like to have $1 million when you retire at age 67, determine the average rate of return needed under continuous compounding. So you know the years, you know t. In this case, we're solving for r. So we know our a, that's right there. Right, that's my a. We know my p. We don't know r. R is what we don't know. But we know t. T is equal to, you want it when you retire at 67, and you minus the 19, and that, so 67 minus 19 is 48. So t is 48. We're just plugging everything in. So I want $1 million. 2, 3, 1, 2, 3, and it's equal to 100,000. So 1, 2, 3, 1, 2, 3. Great. Times my e. R is unknown, but I know 48, so I'm going to write it 48r. And r is what I'm looking for. First thing, I'm going to divide off that 100,000 from both sides. This filters and becomes 1. Cross that one. 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 So that's equal to 10. So 10 is equal to e to 48r. I'm going to use ln. So ln of 10 is equal to ln of e to the 48r. Again, this whole thing can come down in front. So this becomes ln of 10 equal to 48r ln of e. Again, ln of e goes to 1. So that's just 48r. So ln of 10 is equal to 48r. I want to know r, so I'm going to divide by 48. Divide this side by 48. That filters off. So ln of 10 over 48 is equal to r. And then I really just need to plug that in the calculator and I will get some approximation. So r is approximately, again, I'm looking for a rate, so that's fine, divided by 48. 0.04797. So what does this become? So move this over. So this is about 4.8%. Again, approximation. So that would be the average rate I would need to get on that investment. or whatever investment I was using that was continuously compounded. That's the process. Again, we've kind of done this before, but this is the idea of using this. We're going to use this example to set a 0 here and kind of look at that growth. All right. Now we have a population. So this is where we're going to be setting a naught, a P naught, our beginning point. On January 1st, 2000, the population of Texas was approximately 21 million. On January 1st, 2010, the population was 25.2 million. So we want to write a function of the form that P of t is equal to P naught times E to the K to the T to represent the population. And this will be the population P of t of Texas T years after January 1st, 2000. And we're going to round K to 5 decimal places. So first thing, we need to come up with a form. We're kind of given the guide right here, and we're just going to follow that guide. So the population, P of t, is going to equal, well, our P naught is right here. This is our P naught. So that's 21 million. So I'm going to do this in millions. So 21 times E, K, T. But actually my T at this point, since this is the beginning, my T should equal 0. So this becomes 21 times E to the K times 0. Well, K times 0 is 0. E to the 0 gives us that this is equal, at t equals 0, so I guess at t equals 0, this is equal to 21 million, which is great. But we also know that P of 10 years since 2000, so at t equals 0 or 10, P of 10, we need to equal, we know what we need to equal, so we can solve this for K. So we say, okay, well, this equals 21 times E to the K times 10 must equal 25.2. 25.2. Well, if we know that, we can solve for K. So let's do some solving. Let me see. Not a lot of room, but let's see what we can do. First, I'm going to divide by 21. Divide this side by 21. So this piece will come up here. I have E to the 10K is equal to 25.2 divided by 21. And then I'm going to ln both sides. So maybe pull that down too, because I can. So I have 10K ln of E, that's going to go away, is equal to the ln. Remember, if you do ln on one side, you got to do it to the other side. 25.2 over 21. This goes to 1. So I'm really just dividing by 10. Divide this whole thing by 10. So K is going to equal ln of 25.2 divided by 21, all divided by 10, or approximately, we're rounding it to 5 decimal places. So again, we're just pulling on the calculator. We're saying ln of 25.2 divided by 21, close that parenthesis, and then divide the whole thing by 10, and this equals, so my k is 0.01823. So my equation, or my function is really, let me write it up top so I have it, is really, so p of t, now that I found out what k is equal to, this gives me the whole function. It is 21 times e to the 0.01823 times t. That is the real function. This is the growth rate of the population of Texas. At some point it'll follow this for some period of time, and then it'll probably have to have a new function. So B says use the function that we just developed. So this function, this is A. It takes some work to predict the population in January 1st of 2020. So again, all we're doing is saying t equal to 20. Let's see, do I have room to work on that on the other side? No, I don't. Okay. So again, I'm just saying that t is equal to 20. I'm going to plug it in, but I'm actually just going to use the equation. I can just use it as is now, or my expression, and I just replace the t with 20. So this becomes, let me write it out. Let's see. Maybe what I need to do is move that 20 over. So let me do that. So erase. Okay. And then ink. Okay. So this is at equals 20. This becomes P of 20 is equal to 21 times E raised to the 0.01823 times 20. And that is approximately 21 times e to the 0.1823 times 20. Is that 5? That's 5. Okay, good. And then hit enter, and this is approximately 30.2 million people, right? Million. Use the function part A to determine the year during which the population of Texas will reach 40 million if that trend continues. So we can do that. In this case, we're looking for t, but we know what we have 21 times e 0.01823 times t, and we want this to equal 40. So again, we're going to divide by 21. Kind of the way we went through solving it, we're going to divide it by 21. So I have 30.2 all that stuff, then I'll take the log of it. So let me write it down first. Just running out of room. 0.01823t is equal to 40 over 21. Now take the log, the natural log of these, so I can pull this out in front, and that gives me that gives me, let me just, 0.01823t times ln of E is equal to ln of 40 over 21, and then just divide this. This goes to 1 again, so that goes away, and I'm dividing by 0.01823. Divide this by 0.01823, which is approximately, it doesn't tell me what's around, I'm determining years, so approximately this would be ln of 40 divided by 21, close that parenthesis, divided by 0.01823. This is approximately 35. So 35 years added to 2000 would be, again, approximately the year 2035 would be when they would reach, sometime in that year is when they would reach the 40 million population. So that's the modeling. That's the process. Usually in this one, they're asking you to do some steps to get there. Oftentimes they just give you the first two and say, what would the population be here? So they jump right to this. You have to know to find K. You have to know to do that. You wouldn't necessarily need B, but you would still need to do A no matter what, because you have to figure out what K is. All right, let's look at another one. This is a try. I think I'll walk you through some of this just because. A sample collected from cave paintings on an archaeological site in France shows that only 2% of the carbon-14 still remains. How old is the sample? Round to the nearest year. So we know the model, they're giving it to us. The model, why is my parenthesis not showing? That's weird. Only some of them do that. The model for the radiocarbon dating is the Q of T is equal to Q naught times e to the negative 0.000121 times t, where Q naught is the original quantity of carbon-14. So we don't know the quantity, but we do know that it was 100%, right? It was all of the carbon. And we know that after some amount of time, there was only 2% of it left. So if I have 100%, and I'm finding out when it would be 2%, it's kind of like, well, it's not kind of, it is. Q naught is equal to 100%, all of the carbon, keeping it as a percent. And we want to set this equal to 2%. So let's do that and solve. So that says 100% times E of negative 0. Man, I'm going to 1, 2, 3, 1, 2, 1. T is equal to 2%. Same idea as before. I'm going to divide by 100%. Divide this by 100%. Awesome. That filters off. I'm left with e to the negative 0.123121 t is equal to, well, we can actually do 2% divided by 100%. It's really 2 divided by 100, right? Technically, these are each per 100, so those hundreds cancel off. So it's really just 2 over 100, which is 0.02. So I'm going to go ahead and write it as a decimal, 0.02, just because that's a little bit easier. And then I can take a log, and remember that this piece, I'm going to use the natural log, would come out in front of my natural log. So I would have negative 0.123121 t ln of e is equal to the ln of 0.02. And same situation, this goes to 1, right? E to the power of 1 is going to give me e, so that's why it's 1. I can divide by negative 0.000121, and that'll give me the t by itself. I have to divide this by the same thing, 0.00121. So this says my t right now is ln of 0.02 divided by negative 0.000121. So let's plug that in the calculator and see approximately what we get. We're going to round to the nearest year, but let me just kind of approximate out some answers, some of the numbers. So ln 0.02. Let's close that, and then divided by negative 0.123121, and that gives me approximately 3233.766. And we'll just stop there. It does go on continuously. So how old is the sample? We're going to round to the nearest year. So rounding to the nearest year, this is 32,331 years ago. Is when that cave painting was painted, or the material for that cave painting was painted. That's the process. I know that was a try I'm sure you guys were all excited about, but you'll have your own to do in the homework. And is that it? Nope, one more. Apply the logistic to growth. Oh, we just did a decay. All right. So we can also use a logistic growth model, and it's normally written as y equals some c, some positive constant, divided by 1 plus a to the power of e to the negative b times t. And what we see here, this growth model, we have a point of inflection, we have where the rate of change is increasing, and then where the rate of change is slowing down. So this would be like the slope is going quicker, so it's increasing, and then the slope is going down. Our constant, y equals c, is kind of asymptotic for us, and that becomes like the leveling off point. So we're going to apply one of those. This is the population of Los Angeles in millions, and it can be approximated, and that's up in the top right. Again, that didn't show the parentheses. That's weird. By a logistic growth function where t is the number of years since 1900. So this is using it since 1900. and it wants us to evaluate if we put in p of 0 and interpret that meaning. So first, let me say that if I plug a 0 in for t, the negative 0.052, and again, I'm looking up here, this will go to 0. E to the power of 0 is just 1, so this becomes 3.194 divided by 1 plus, right? So in 1900, this would tell me what that is. This is my P naught. So this is 194 divided by 15.589. And this is in millions, but this answer is technically 0.205 millions. So it's not even a million people. So in the 1900s, Los Angeles did not have a million people living in it. Okay, so interpreting its meaning in the context of this problem is to say that in 1900, Los Angeles' population was less than 1 million, right? It is less than 1 million. We can use this function to predict the population of Los Angeles on January 1st, 2016. So first we need to figure out what that t really is. And the t of that would be 2016 minus the 1900. That's going to tell us what the year is. So this is 6, 1. We have to borrow. So that's 1. And that's 10. So that's 1. So this is P of 116, right? This is P of 116. And then, so that tells us we're somewhere over in this area. And our modeling has something just less than 4 million. So let's see what this comes out to be. And again, I'm just plugging it in the equation that we've been given. So 3.194, 1 plus 14.589 times e to the negative 0.052 times 116. And again, I'm just going to plug all that in the calculator and see what we approximate to get. Some of this we don't have to actually do something else with it. So 3.194 divided by, and here I'm going to open a parentheses. I want to be clear that I'm making sure I'm going to get all the pieces. And this is 1 plus 14.589 times e raised to the negative 0.052 times 116, and then I need to close that parenthesis and then hit enter. And I'll check and make sure I did that right. I got, so let me tell you what I got. I got 3.086. So that's what I got. Does it make sense? Well, yeah. I mean, clearly I'm not up at 116. I'm not up at the 4. I am maybe farther up than I thought I would be. So I'm just going to double check that I have this right in my calculator, just to double check. Luckily I can go back and look at it. Okay, so let's see. Negative 0.052 times 116, that's right. Times the, nope, I'm good. All right. Yeah. So that's approximately, this is in millions of people. Interestingly enough, we can't actually look at 2016 because the census happens every 10 years. So we could look at 2020, we could look at 2010, but we can't actually look at 2016. So that's pretty interesting. All right. There we go. We've covered it all. That is the end. All right. You guys will have everything as soon as all these get uploaded. And we'll go over some other stuff tomorrow. And yeah, these should go live, well, by tomorrow, I hope. We'll see how it goes. All right. Keep plugging away.